Think about how artists work, stroke by stroke, building up an image, or chemists synthesizing molecules step by step. There's this dynamic order, even when it looks a bit chaotic,
Yeah, it's fascinating. And that kind of sequential process is something machine learning is getting really good at modeling.
especially with autoregressive models, right? ARMs, I know they're huge in text generation.
Exactly. Arms are fantastic for things like text because there's a natural flow. You predict the next word based on the ones that came before. It captures that inherent sequence.
Right. But that's where it gets tricky, isn't it? Text is linear. What about stuff that isn't? Like images or the complex 3D structure of a molecule.
That's the core problem. Traditional arms rely on a fixed generation order you decide beforehand. I'm generating pixel 1, then pixel 2, or whatever.
And that feels artificial for data that doesn't have one single correct order.
Precisely. Imposing an order, like, say, scanning pixels left to right, top to bottom, might work okay, but it might also miss the bigger picture or force the model down weird paths. It's a constraint that might not fit the data's real structure.
So people tried to fix this. I remember reading about any order arms, AO arms. What was the idea there?
Well, the idea with AO arms was basically to embrace the ambiguity. Instead of a fixed order, they tried to train the model to work with any possible order.
Any order, how does that work?
They treated the generation order as a kind of hidden variable and assumed a uniform distribution over all possible permutations. So every sequence of generating the data points was considered equally likely during training.
Okay, so train the model to be a jacks of all trades for ordering.
You could put it that way. The goal was maximizing the expected log likelihood over all these different random. It's actually related to some ideas in diffusion models, too, this sort of sequential revealing or unmasking.
Unmasking. Let's hold that thought. So AO arms sound clever, but the paper suggests he didn't always hit the mark performance-wise. Why not?
Well, think about it. Training a model to be equally good at predicting the next piece of data, given any possible subset of previously generated data, that's a huge task.
Right. The number of possible orders, permutations, it just explodes, especially for high-dimensional data.
Exactly. It's incredibly complex, and the model doesn't learn any preference for orders that might be, more efficient or meaningful for that specific type of data. It aims for universal competence, but maybe lacks deep expertise in any particular strategy.
Okay, that makes sense. So fixed orders too rigid, any orders may be too unfocused, which leads us to the main topic today, learning order autoregressive models. Low arms.
Precisely. This is where the key innovation lies. Low arms don't just accept any order, they learn which orders are good.
They learn the order. How?
Instead of that uniform distribution over orderings like in AO arms, low arms introduce a learnable probability distribution over the sequences. They call it the order policy.
An order policy. So it's like a little decision maker inside the model.
Kind of, yeah. Crucially, this order policy isn't static. It decides which dimension, which piece of data to generate next, based on the data it's already generated up to that point.
Ah, so it's context dependent. The order emerges during generation based on what's already there. That sounds much smarter.
It is. The model learns from the training data what constitutes an effective generation strategy, what order makes sense given the partial structure it's built.
And the paper applies this to generating molecules with pretty impressive results, state of the art even.
Yes, the molecular graph generation results are a key part of the paper. From an academic perspective, it's a great test case because molecules are complex, non-sequential structures. And yes, they achieve state-of-the-art results on benchmarks like QM9 and ZINC250k.
Which suggests this learned order isn't just a gimmick, it's actually finding meaningful ways to build these complex things.
Exactly. It implies the model can discover and exploit useful structural patterns to guide its own generation process.
Okay, so that's our mission for this deep dive, then really dig into how low arms work, specifically this innovation of learning the generation order, and understand why that makes such a difference, especially for data without that natural built-in sequence.
Sounds good. Maybe we should start by quickly recapping the basic autoregressive idea, just to set the stage.
Good idea. So standard autoregression takes a data point, let's say a vector math BF dollar with components $90 to XL dollar.
Right, and it factorizes the joint probability, P dollar math BF dollars, into a product of conditional probabilities. If you fix an order, say 1 to L, it's PX1 times PSA $3 times PXL dollar, and so on.
PXL $1, L dots, XL $1.
That chain rule decomposition.
Exactly. And the problem we keep circling back to is that for many data types, there's no single best ordering 1 to AL dots L. Yeah, for an image, do you do rows, columns, spirals? Focus on edges first. It's not obvious.
Precisely. So AO arms, as we said, tried to average over all $L possible permutations. Let's call it permutation sigma dollar. They basically calculated the probability as the average probability over all possible sigma dollars.
So the training tried to make the model good, on average, across all these random orders.
Yep. And mathematically, this training objective, maximizing the expected log likelihood over all permutations, turns out to be equivalent to maximizing a lower bound, a variational lower bound, on the true data likelihood, where the permutation itself is the latent variable.
Okay. Now, you mentioned unmasking earlier in the context of AO arms and diffusion models. How does that fit in?
Ah, right. It's a useful way to frame generation, especially for discrete data like categories or pixels with specific values. Imagine you start with everything masked, you don't know any values.
Like a blank slate.
Exactly. And the generation process involves picking a mask dimension, unmasking it by assigning it a value, like choosing a pixel color or an atom type, then picking another mask dimension, unmasking it based on the first one, and so on.
Until everything is unmasked and you have your final data point.
Correct. So the sequence in which you choose which dimension to unmask, well, that is the generation order we've been talking about.
Got it. So choosing the order is choosing the sequence of unmasking steps.
Yes. And while this sounds a bit like diffusion models, which often have a masking forward process and an unmasking reverse process, these low-arm guys focus purely on the generation, the unmasking part. They don't define an explicit forward process.
Okay, interesting distinction. So framework established. Fixed order RMs have limits. AO arms try to handle all orders but struggle. Now, low arms, learning the order. Let's get into the mechanics.
Right. So the core is replacing the uniform distribution over orders with this learnable order policy. Here, math_BFZ is the latent variable representing the order Z1, L dots, ZL, where Z dollar is the index of the old dollar dimension generated.
And the crucial bit is how PF is structured, right? You said it's context dependent.
Exactly. It factorizes autoregressively itself. So the probability of picking index Z-roller as the next dimension depends on the previously chosen indices and the actual data values already generated according to that partial order, math_BFC, and the actual data values already generated according to that partial order, given what it's already built. Precisely. It's learning a dynamic strategy. Now, training this involves maximizing the log likelihood of the data, but because the order math_BSBF, you technically need to sum over all possible orders.
Which is that Eldora problem again. Impacted.
Right. So standard approach, use variational inference. They introduce another distribution, a variational distribution, Q dollar.
Okay, wait. Two distributions over orders. The order policy P dollars and this variational one Q dollar.
Yes.
The order policy P-dal is what the model uses during generation. The variational distribution Q dollars is used during training. Its job is to look at a complete data point and try to infer likely orders math_PF that could have generated it.
Ah, okay. And how is Q dollar structured?
It also factorizes autoregressively, Q dollars probia.
But notice the key difference in conditioning.
Let me see. P dollar conditions on the partially generated data, math_PF, while Q conditions on the full data, math_PF.
Exactly. Because Q dollar sees the whole picture during training, it can learn to recognize sensible generation pathways for complete data points. It then helps teach the order policy P dollar, which only sees the partial data during actual generation.
Correct. The ELBO involves an expectation over order sampled from Q dollar and a Kate-L divergence term that encourages the order policy P dollar to stay close to the variational approximation FPF.
Correct. The ELBO involves an expectation over orders sampled from Q dollar and a KL divergence term that encourages the order policy PL math_BF.
And how do they actually compute that expectation or its gradient? Still seems tough with L possibilities.
They don't compute the full expectation. They use stochastic estimation. During training, they sample orders from the variational distribution grows up to it, is there to receive the partial distribution.
Just sample one order per data point.
They actually sample an index $, and a partial order math-BF data. The paper mentions using reinforced gradient estimation, specifically an estimator called RLOO that uses two samples, to handle the fact that sampling discrete orders isn't directly differentiable.
Right, reinforce for discrete latent variables. Okay. And it's neat that if you set both $P$ and $Q$ to be uniform, you basically get back the AO-arm objective.
Exactly. It shows low arm is a direct generalization. AO arm is the special case where you don't learn the order.
So the training algorithm, algorithm 1 in the paper, samples two orders, MathBF $2 for a given data point. MathBF computes this reinforced gradient estimate for the ELBO and updates the parameters.
That's the gist of it. And then for generation, algorithm 2, you sample the next dimension, $, from your learned policy, PBay, and then you sample the actual data value using a separate classifier network conditioned on the history MathBF.
Okay, let's talk about the networks. How are $Q$ and the classifier actually built? The paper mentions Placket-Loose for $Q$.
Yes, the Placket-Loose model is a common choice for modeling probability distributions over permutations or rankings. It's parameterized by the vector of scores, lob bits, $G, which are typically the output of a neural network that takes the data MathBF as input.
So a network looks at the data MathBF dollars and output scores for each dimension, and Placket-Loose turns those scores into a probability distribution over generation orders.
Pretty much. The probability of picking dimension $P$ next, given you haven't picked it yet, is based on its score relative to the scores of other remaining dimensions. It's computationally efficient to sample from, too, which is important for training. They mention using the Gumbel-Top K trick for parallel sampling.
Speeding things up. Makes sense. And the classifier FBF dollar, the one that predicts the actual value of $.
That's another neural network. It takes the partially generated data, MathBF, as input and outputs probabilities for the possible values of accessors. The specific architecture would depend on the data type, like graph convolutions for molecules.
And you mentioned different ways to set up these networks, shared torso versus separate.
Right. Shared torso means the network producing the logits for $Q$, the network for the order policy $P$, and the classifier $F$ might all share most of their layers, their torso, only diverging at the final output layers.
More parameter efficient, maybe.
Could be. The separate approach uses distinct neural networks for each component, more parameters, but potentially more flexibility for each part to learn its specific task.
Interesting trade-off. Okay, let's pivot to the application. Molecular graph generation. How do they represent molecules?
They used dense adjacency matrices. So a matrix where entry $I tells you about the bond between atom $I and atom $, plus information about the atom types themselves. The task is to generate this matrix and the atom types.
Got it. And the evaluation, they use QM9 and ZINC250k datasets. What metrics mattered most?
Yeah, standard benchmarks, key metrics were validity, does it represent a real chemical structure? Uniqueness, are the generated molecules different from each other? And critically, FCD, Fréchet ChemNet Distance.
FCD. I know that one's important. It measures how similar the distribution of generated molecules is to real ones, right? Not just individual molecule quality.
Exactly. That uses pre-trained chemical feature extractors to compare the overall statistical properties of the generated set versus the real set. A lower FCD is better, meaning the generated molecules are chemically realistic as a population.
And the results on QM9, low arm did well.
Very well. The low-arm variants, especially one called low-arm separate Corso networks, significantly outperformed the baseline AO arm and achieved state-of-the-art FCD scores on QM9 at the time.
And they also got high validity and uniqueness.
Yes, which suggests the learned orderings weren't just random, but were consistent enough to produce plausible and diverse molecules. The low FCD really underscores that the quality of the generated distribution was high.
What about Xenon C250k? That's a bigger, tougher data set, right?
It is, and the improvement there was even more pronounced. Low arm showed really significant gains over AO arm and a biased version of AO arm across all metrics, validity, uniqueness, and especially FCD.
So learning the order seems even more important when the data gets more complex.
That seems to be the case. The author suggests that a learned order helps mitigate error accumulation. If the model learns to generate the more certain, maybe structurally key parts first, it builds a better foundation, leading to fewer errors down the line compared to a random order.
That makes intuitive sense. Did they try tweaking the generation process, like with top P sampling?
They did. Top P sampling, where you only sample from the most likely next candidates, often improved validity, making sure more outputs were chemically correct.
But maybe at the cost of diversity or FCD?
Sometimes, yeah, there can be a trade-off. Interestingly, they found the O-arm with separate networks was more robust to top P sampling. Its FCD didn't degrade as much. This hints that its learned order policy might already be good at prioritizing dimensions where the model is more confident.
Fascinating. And they had that MNF example in the appendix, too, just to visualize the learned order.
Yeah, a nice qualitative illustration. For M&S digits, the low arm learned to generate the border pixels first, then fill in the actual digit.
So, like, establishing the campus boundaries before drawing the main subject.
Sort of, yeah. It suggests a strategy of handling the less ambiguous parts first, providing context for the more variable parts later.
And for molecules, they found a consistent pattern in the learned order, too, didn't they? Something about skeleton first?
Yes, a really interesting finding. They observed a fairly consistent three-stage process emerging from the learned order policy. First, building the basic atomic skeleton, then kind of infilling bonds, maybe placeholder bonds initially, and finally specifying the actual atom types.
Wow, so it's not just learning an order, it's learning a chemically plausible strategy for construction. That's a powerful result.
It really is. It suggests the model is capturing some deeper structural logic of molecules through learning the generation order. They did some analysis in the appendix looking at this consistency more formally.
Plus more ablation studies looking into architectural choices and sampling methods. Sounds very thorough.
Definitely, they really dug into the details.
Okay, so let's wrap this up. The absolute key echoey here seems to be low arms' ability to learn the generation order. That's the big leap beyond fixed order arms.
Without a doubt, that learned, context-dependent order policy is the core innovation, allowing it to tackle data without a natural sequence much more effectively.
And the results speak for themselves: state-of-the-art FCD in molecular generation, strong validity, and uniqueness. It shows this learned strategy leads to genuinely better quality samples.
Yeah, the implication is that these models can autonomously figure out sensible, consistent ways to generate complex things like molecules, which is pretty exciting.
Of course, there are always next steps. They mentioned improving validity further, maybe incorporating chemical rules into the order learning.
Right, and exploring more efficient representations than dense matrices, applying it to other areas like protein design or maybe even high-resolution image generation. Lots of potential future work.
Definitely. Which leaves us with a final thought for our listeners. Think about other complex sequential processes out there, maybe in biology, engineering, even art or music. Could this idea of learning the order of operations, dynamically adapting the sequence based on context, unlock new ways to model and generate things in those fields too?
It's a really interesting question. What other kinds of data are just waiting for a model that can figure out the best way to build them, step by step? Makes you think.